Velocity and gravity physically alter the flow of time. When mass and speed enter the equation, the rigid progression of seconds and minutes flexes. Traveling into the future is a measured physical reality. If a person leaves Earth on a ship traveling at 90% the speed of light for 10 years, they will return to find 23 years have passed on the ground. They arrive 13 years in the future. The same physics allows Muon's subatomic particles created in the upper atmosphere to survive longer than their standard decay rate simply because they are plummeting toward the surface at near light speed. In 1971, researchers synchronized atomic clocks and placed them on commercial aircraft. When those clocks were flown around the world and brought back, they registered slightly behind the ones left on the ground. The delay was measured in nanoseconds, exactly matching mathematical predictions. Global positioning satellites in orbit travel fast enough to slow their onboard clocks by 7 microseconds a day, while the weaker gravity at that altitude speeds them up by 45 microseconds. Without daily mathematical corrections for these exact relativistic effects, the entire GPS network would fail, drifting by 10 kilometers every 24 hours. Space and time stretch and compress around us every day. The equations dictate the behavior of our phones and airplanes. This forces a specific question. If the math holds true here on Earth, what happens to the fabric of reality when it is subjected to the absolute extremes of the cosmos? When a star 25 times the mass of our Sun dies, it collapses under its own weight. The mass compresses into a single point, warping the surrounding space into an inescapable gravitational funnel. Around this collapse is a mathematical boundary where the velocity required to escape exactly equals the speed of light. There is no physical wall or surface here. Relativity dictates two different timelines at this threshold. From a safe distance, an observer watching an astronaut fall toward this boundary would see them slow down and their image shift toward red, eventually freezing indefinitely. For the falling astronaut, time progresses normally as they slip past the edge. Once past the threshold, the physical consequences take hold. Gravity pulls the astronaut's feet far stronger than their head, stretching them vertically and compressing them horizontally in a process known as spaghettification. This is a photograph of M87 capturing the shadow of a supermassive black hole. The ring of light precisely matches the dimensions mapped out on paper over a century ago. Detectors have also measured the gravitational waves of black holes colliding in deep space, confirming the physical properties of these objects. The equations predicted extreme gravitational traps decades before humans possessed the technology to observe them. Because the math accurately mapped the most violent regions of the visible universe, physicists are forced to confront the unproven, far stranger solutions hidden in the same formulas. If space bends under gravity, equations ask if it can fold. In 1935, the Einstein-Rosen bridge emerged. 2 points separated by billions of light years across a flat plane could link. Piercing a hole through folded space creates a direct shortcut between distant regions. The math works, but it contains a critical flaw. The original equations show that this bridge is highly unstable. It opens and collapses so rapidly that nothing, not even a beam of light, could make the journey before the tunnel crushes shut. To force the throat of the tunnel to stay open, the structure would require a substance with negative energy density. This kind of exotic matter violates the established energy conditions of classical physics, running contrary to everything observed in nature. The geometry of relativity technically allows space to fold into a shortcut, but the universe appears to withhold the physical materials required to construct it. While traveling into the future is a verified component of spaceflight, equations for traveling into the past introduce severe complications. The framework holds solutions known as closed time-like curves, trajectories that curve back on themselves, returning a traveler to their exact starting point in both space and time. In 1949, mathematician Kurt Gödel discovered the first of these solutions, demonstrating that a rotating universe mathematically permits these closed loops. Other models show similar curves could exist inside rotating black holes. Moving backward through time breaks the logic of cause and effect. If a person travels to the past and stops their grandparents from meeting, that person is never born. If they are never born, they cannot make the trip to the past. Theoretical physics seeks a mechanism to prevent this breakdown in logic. Stephen Hawking proposed that nature protects the order of time. Calculations suggest that the moment a closed time loop attempts to form, quantum fluctuations would surge into infinite energy, destroying the structure before it could be used. The equations for time travel force a collision between mathematical possibility and the basic structure of logic. It appears nature deploys quantum mechanics as a defense mechanism to keep the past firmly out of reach. The true test of a scientific theory is finding exactly where it stops working. For general relativity, that edge is found at the dead center of a black hole and at the first moment of the Big Bang. At the core of a collapsed star, the equations compute a state where all mass is crushed into a point of zero volume. According to the math, the density of the matter and the curvature of space become infinite. In theoretical physics, infinity is not a physical place or an observable state. It is an error message signaling a mathematical failure at the singularity. The rules of relativity simply break down. The tools that accurately measure GPS satellites and map the shadows of supermassive black holes lose all ability to describe what is happening. In reality, these equations are not a complete answer to the universe. They are a highly accurate map that eventually guides us to a cliff, marking the exact border where the map itself becomes useless. The structural problem lies in a deep incompatibility. Relativity describes a continuous, smoothly bending fabric of space and time, while quantum mechanics operates on a tiny scale where energy and matter exist in discrete, unpredictable chunks. The two most accurate operating systems in physics cannot run at the same time. The scale of what we do not know is staggering. Together, dark matter and dark energy dictate the expansion and mass of the cosmos, yet their physical nature remains unknown. Everything we can observe and measure accounts for barely 5% of the universe. The final unresolved clash happens as black holes evaporate over time. Quantum mechanics strictly forbids the destruction of information, yet relativity suggests that whatever falls into a black hole is permanently erased when the hole eventually vanishes. Albert Einstein did not live long enough to see a black hole photographed or to watch a machine register the gravitational waves of colliding stars, yet his calculations predicted those exact events before they were proven, and they successfully predicted their own structural limits. By defining the precise behavior of space and time, relativity gave us the modern universe. Its greatest triumph is that it points directly to the breaking point, illuminating the exact boundary where the next revolution in physics has to begin.